Hi, this is Kenny, and let's talk about a more advanced kinematics equation. This is the time-independent kinematics equation. And this one is one that actually doesn't have time in it. All the others that we've seen have had some time factor in it, but this one doesn't. What we got is the final velocity squared equals the original velocity squared plus twice the acceleration times. Really, you should think about this as maybe displacement, but d is very common to use distance for, but let's think more about displacement. And an alternate version of this looks something like this, where everything's the same except here they're talking about the displacement from where you are from where your original starting point was. But when would you use this equation? Well, I would use it either if I don't know the time or simply don't care what the time is. I'm solving for something else and I don't need to know the time. So let's take a look at one of these problems. Here's the first one. We've got a boat going 20 meters per second and accelerates at 3 meters per second squared, or 3 meters per second, until it has a velocity of 32 meters per second. How far does the boat go during this acceleration? Well, we've got some information here, so let's go ahead and map it out. We've got a original velocity of 20 meters per second. We've got an acceleration of 3 meters per second squared. It goes up to this speed, so that's our final speed of 32 meters per second. And we actually just want to know the acceleration. So, do we need to use our new formula, or could we do it using the others? Well, let's compare. I'm going to first use some time-dependent kinematics equations to solve this one and see what we get. All right, so how do we determine if we're going to use this equation or another one? Well, for this example, I want us to compare those two. So I want to solve it both ways. Once with the time-dependent equations and once with the independent equation that I showed you on the previous slide. So let's start off with this. I've got A, VF, and VO. So if I'm looking at my time-dependent equations, it looks like this one would be the way to go to actually figure out what the time is. Acceleration is 3, final velocity is 32, original is 20. We got to solve for t. Super secret metric, where we swap those out. We get a time of 4 seconds. And now we can use that, because we're looking for distance, with this one. D equals V0t plus 1/2 AT squared. Original velocity is 20. The time we just found is 4. Plus 1/2, acceleration was 3, times 4 squared. And so we just work through the problem. That's going to be 80 plus, if we look at this, we've got 16, because 4 squared is 16, times 3 divided by 2 gives us 24. So this object should have traveled 104 meters. So that's using our O time-dependent equations, but I was never asked for time. I just need to know how far the object went. So let's use our new one. VF squared equals VO squared plus 2AD. Final velocity was 32. That's got to be squared. Equals original velocity 20 squared plus 2 times 3D. So let's do that. 32 squared gives us 1024. 20 squared is 400 plus 6d. Now we got to solve, move the 400 over, so we're going to subtract 400 from both sides. So that gives us 624 equals 6d. Divide by 6, and we get 104 meters equals the displacement or distance, and they match. So here we had to actually do 2 steps, while this one just ends up being one equation that we have to use. So that's the power of using this. And again, I'm never asked for time, so I don't care. So this way I go straight to the answer. Let's look. Let's look at this one. So we got a car traveling 40 meters per second, comes to a stop in 15 meters. What's its acceleration? So we've got original velocity of 40 meters per second has a distance of 15 meters. We want to know the acceleration. And we know another piece of information. It came to a stop. So that means our final velocity is 0. Let's use our new equation. Vf squared equals Vo squared plus 2AD. So if we've got this, final velocity was 0. Original velocity is 40, but that's squared. Plus twice. Acceleration we don't know, but the distance is 15. So we got 0 equals 1600 plus 30a. Move that over. Now, let's go ahead and divide 1600 divided by 30. I got to remember that this is negative, so negative 3.3 repeating meters per second squared is our acceleration. See, quick, easy calculation with that one because I don't know time and I don't care about it. Last one here. A plane's going 50 meters per second. So we've got an original velocity of 50 meters per second. Accelerates at 6 meters per second squared over a distance of, or we can call it a displacement, I guess, of 180 meters. And we want to know the final velocity of the object. Well, we're actually looking for Vf this time. So let's use our new equation. Vf squared equals Vo squared plus 2AD. So we're looking for this. Original velocity is 50, but that's squared, plus 2 times 6 times 180. All right. So let's do our math here. So we got 50 squared. Plus we've got this, so we've got 2 times 6 times 180 gives us this. And we simply add them together. So we get Vf squared equals 4660. But we don't want Vf squared, we want V. So we're going to take the square root of both sides. And we get 68.26 meters per second is the final velocity. Now, what if we try to do one of the other equations? I'm looking for Vf squared, so I can do A equals Vf minus Vo over T. Well, A is 6, Vf we don't know, Vo is 50, and time we also don't know. Well, that means we have to use the big long one. D equals V0t plus 1/2 AT squared. Distance is 50. Original velocity is, actually, distance is 180. Good thing I made a list. Velocity is 50 plus 1/2 a is 6 t squared. So 180 equals 50 t plus 3 t squared. Oh, we would have to use the quadratic formula. I really don't like the quadratic formula, so I'm just going to stick with that and not worry about it. See, this way you actually can save a lot of time because you wouldn't have to use that quadratic formula. Good avoidance technique. All right. Thank you, and I'll see you in another video. Goodbye.